Okay, onwards and upwards with vectors, and today we're going to look at the angle between two vectors. We discovered in the last lesson about the dot product and how we could use it and what it meant really, and what I really want you to, I guess, understand really about the dot product is that it takes the dot product of two vectors. Well, it's like a projection of one vector onto the other. So this vector projected down onto this vector. So if we're going to call this A and this vector B, then what this represents here, this element of it, I didn't get my highlighted pen as I'd wanted. That element of it there is what we would call the projection of A onto B, or if you like, it's the magnitude of A in the direction of B. So that distance there, which is actually equal to, if that's theta, it's equal to A cos theta. That distance there multiplied by the magnitude of B, well, that gave us the dot product, right? That's what the dot product of this is. It's a measure of parallelness. So to the effect of, if two lines are perpendicular, two vectors are perpendicular, their dot product will be zero. They've got no parallelness. There's no parallel direction in common. Little bit like when you talk about gradients, or then there's no gradient. It's a horizontal line. If you can't define the gradient, it's a vertical line. So it's in a similar way. This is a measure of parallelness of two vectors. And we're going to move on to the scalar product next. Scalar product. This is a scalar product. Dot, scalar, synonymous. I meant the vector product, or the cross product, which is actually the opposite of this, and it's a measure of the perpendicular relationship between the two vectors. But we'll come to that. So the dot product, well, it helps us as I'll write down in a more formal way right now. The dot product. So u dot v. Well, yeah, we know how to calculate that. Remember, it's the sum of the products of the components of the vectors, but it's also the magnitude of u by the magnitude of v by cos theta, as we just looked at. So this is by first principles, really, and that's equal to, well, we know it to be, if it's in component form, it'll be u1 v1 plus u2 v2 plus u3 v3. Now in this example, u is equal to 2, negative 3, 4. So my u1 is 2, my u2 is negative 3, my u3 is 4. V is equal to, what do we got? 1, negative 1. And so therefore, my dot product of uv is 2 times 1, which is 2, negative 3 times negative 1, so that's plus 3, 4 times negative 1, so that's minus 4, so it's just 1. So my dot product is 1, and so I can use that now to find my angle between the two vectors, right? So now let's move across here and use that. So cos theta, making cos theta the subject, I've got u dot v over the product of the magnitudes of u and v. So u dot v we've just calculated. Now, what's the magnitude of u? 4, 9 is 13, plus 16 is 29, by 1, 2, 3, 29 root 3. So this is 1 over the square root of 87. So theta will be the inverse of this amount here, which we can calculate, which gives us 83.8 degrees to 3 significant figures. Okay, there's our angle between those two vectors. A bit of a recap of dot products while we're at it. Let's do another example. Okay, so let's cut straight to the chase with this example. Feel free to pause and do the question yourself. Cos theta equals, now it's my dot product of uv. So I'm just going to write it out because I like to get the hang of this formula. uv. Right, the more times I write it out, the more comfortable I'll be with it. Right, so I've got 3k plus 2k as a dot product. Now my magnitude here of u is 1 plus k squared, square root of 1 plus k squared, and my magnitude of v is 4 plus 9k squared. Right, fair bit going on here. Cos theta equals, now I'm told that the angle is 60 degrees. Right, find the values of k. There's a little tip there. We might be looking at more than one. Now cos 60, right, I know a little bit about this. Cos 60, 60 is this angle here. This is root 3, this is 1, this is 2. So cos 60 is a half. So I can therefore say that 1/2 is equal to all this business. See if we can tidy this up a bit. 5k over square root times square root. So I'm probably going to be running this through, multiplying these together and getting a great big square root 30 thing here. So I'm looking at 4 plus, that's 9k squared plus 4, 13k squared. Plus 9k to the power of 4, all under there. Okay, let's see what we have now. So 9, if we look at the square root, it's 9k to the power of 4 plus 13k squared plus 4, and that's going to be equal to 10k. This might turn out to be a GDC exercise. Squaring both sides, 9k to the power of 4 plus 13k squared plus 4, that's going to have to equal 100k squared. So therefore, 9k to the 4 minus 87k squared plus 4 is equal to 0. This looks reducible to a quadratic actually. So if I let k squared equal to m, for instance, if I just make that little substitution, then I'll be able to say that 9m squared minus 87m plus 4 is equal to 0. I can get my quadratic formula out perhaps, or let's just have a look. Okay, so we needed to finish this off via the GDC just by graphing this quadratic here, finding the points of intersection with the x-axis, therefore solving for m and therefore k squared, taking the positive square roots. Obviously, k is not going to be negative. Why not? Since we have an acute angle here, then cos theta must be positive, which means my 5k here has to be a positive value. So we can only accept positive k's, and so therefore 0.214 and 3.1 are our solutions. Okay, exercise 11k for some more practice, questions 1 to 5.